In this problem, we will assume that a material is quite ductile, so that plastic and total strains can be taken as equivalent, as you can see in the problem. And also, equation 3.26 will become true stress is equal to H times true strain to the power of N. In part A, our goal is to show that the exponent N is expected to be equal to the true strain at the engineering ultimate stress point. Let's start writing the equations for true stress and true strain. As you can see in your notebooks, true stress, which is sigma bar, is equal to the engineering stress times 1 plus engineering strain. Furthermore, true strain, which is shown as epsilon bar, is equal to the natural logarithm of 1 plus engineering strain. Here, our goal is to write true stress in terms of true strain so that we can find a relation between the given equations. We can say that the exponential of true strain is equal to 1 plus engineering strain. We will substitute this equation into the equation of true stress so that we will see true stress is equal to the engineering stress times e to the power of true strain. In the question, it is given that the true stress is equal to h times true strain to the power of n. And we found that it is also equal to engineering stress times e to the power of true strain. So that the engineering stress becomes equal to h times true strain to the power of n over e to the power of true strain. At the ultimate strength point, this equation will have a maximum. This means that when we take the derivative of this equation with respect to the true strain, it will be equal to 0 at some point. So we can say that the derivative of engineering stress with respect to true strain is equal to h times true strain to the power of n over e to the power of true strain times n minus true strain, and this will be 0 at the maximum point. To obtain 0, we can say that n should be equal to true strain. And since this is at the ultimate strength point, the true strain will be epsilon bar u. Now we can move to part B. In this part, we will use table E3.1 and example 3.2 and again example 3.3. According to these examples and tables, when sigma u is equal to 395 MPa, the true strain at the ultimate strength point will become 0.21.03. You can find this data in the table E3.1. And according to example 3.3, n is said to be .2117. As you can see, at the ultimate strength point, the true strain is approximately equal to the strain hardening exponent n. And we can also calculate the error to be sure. It will be equal to 0.2117 minus 0.2103 over 0.2103, and it is approximately 0.7%. So it is not much, and we can say that they are almost equal. Let's talk about part C then. From our derivation for part A, we will write an equation for estimating the ultimate tensile strength from H and N. And we will compare this estimate work for the AISI 1020 steel of example 3.1, 3.2 and 3.3. So, from part A, we can say that the engineering stress is equal to H times true strain to the power of N over E to the power of true strain. And we also say that at ultimate stress point, the true strain is almost equal to strain hardening exponent, which will give the ultimate strength is equal to H times N to the power of N. We can write N instead of the true strain, and it will be again over E times E to the power of N. For AISI 1020 steel, from example 3.3, it is given that H is equal to 662.6 and the strain hardening exponent is given as 0.2117. So when we substitute these values into the equation we found, we will see that sigma u is equal to 385.98 MPa. And from table E3.1, we can obtain the ultimate strength value as 395 MPa. Again, these values are almost the same, but let's compute the error. It will be equal to 395 minus 385.98 over 395, and it will give an error of 2.28%. So we can say that this estimate works well for AISI 1020 steel.